Let's say it takes $10 to go out to eat at a particular restaurant, and you have $9. Unfortunately, that means you can't go out to eat. Let's also say that I'm trying to go out to eat, but I can't check my bank account right now. However, I know for a fact that I have less money than you. So, can I go out to eat? Definitely not, right? I have less money than you, and you don't have enough to go out to eat at the restaurant, so I also don't have enough. This is very similar to the logic of the direct comparison tests. You can sit here and memorize a table that looks like this, or you can think of it as this kind of comparison. Let me explain. A positive infinite series converges because its terms get small enough fast enough. If the terms don't shrink fast enough, it diverges. Say this is the graph of a convergent series, or at least its sequence made into a function. And this is the graph of another sequence, right below the first one. It's below it because its terms are smaller, but notice they're still positive. Alright, here's the kicker. Since a series converges due to the speed it's approaching zero, and this one shrinks faster, it's smaller after all, it has to be convergent too. This is why we call it the direct comparison test. We are directly comparing two series, and we know the convergence of one of them. This actually works in reverse too. If we know a series is growing too quickly to be convergent, its terms are too big, it's really divergent, and we know another series has bigger terms, then the second one is definitely divergent. This logic itself gives us a convergence test. If we want to test a series, we can try to compare it to another series, something more familiar. Now, often that first series, the one we know is convergent or we know is divergent, isn't just given to us. We sort of have to pull it out of thin air. Let me show you what I mean. Take a look at this series. It's usually a good idea to compare it to something similar to it. So, does this look like something we know? Well, notice that if you ignore the other terms in the numerator, and then simplify, it ends up being very similar to the harmonic series. And this is good news, because the harmonic series is famously divergent. So, all we have to do is prove that our series is strictly greater than the harmonic series, or a multiple of it, and we'll know that ours is also divergent. And when I say greater, I mean literally greater than, like with a greater than sign and everything. This can take a good deal of algebra sometimes, so feel free to pause if you didn't understand the step. Since our series is greater than the harmonic series for positive n values, then it's also divergent. We got a result. Done. But there's one problem. What if it weren't greater? What if it were less? Being less than a divergent series, unfortunately, tells us nothing. Lots of things are smaller than a divergent series, including both convergent and divergent series, so we're stuck. It still feels like we can do something, though. Our function is so similar to the harmonic series, after all. Luckily, there is another option. If you've already identified a series that is probably similar, you can use a different comparison test. This one's called the limit comparison test, and it has to do with a limit, naturally. You'll still use those two series, the one you're testing and the one you know about, but this time you're finding a limit of their ratio, like this. Specifically, you'll put the series you're testing in the numerator and the series you're comparing it to in the denominator. Their sequences, that is. You'll put that into a limit and evaluate it. If that number is positive, but still finite, then the series both converge or diverge together. The size of the number you get doesn't matter. It could be 5, it could be 5 million. As long as it's a positive, finite number, the rule holds. So, if you know the comparison series converges, then you also know that the series you're testing converges. If the comparison series diverges, then your series diverges. Think of the limit comparison test as the glue. If you glue them together by using the test, then they have to stick together, doing the same thing. The limit comparison test often works where the direct comparison test fails, so make sure you know how to use it. Either way, both tests will require you to come up with another series that you can compare it to. It has to be a series that you know its convergence, like whether it's convergent or divergent, so studying the other tests can actually make you better at comparison tests. Try some practice problems and take a look at our other videos about convergence tests to learn more about those. Good luck! Bye!